There are three different processes that we're going to lay out explicitly how to calculate the change in entropy during each process. So to start with, let's look at latent heat. So we know that for a latent heat process, that occurs at constant temperature, which means I can calculate the change in the entropy in moving from state A to state B is going to be Q, the energy transferred into or out of the system as heat during my latent heat process, divided by T, the temperature at which that occurs. So since I calculate Q for a latent heat process as plus or minus mass times a latent heat value, then this gives me the way that I can calculate the change in entropy during a latent heat process. One thing I want to explicitly remember, of course, is that the temperature here has to be given in Kelvin. So as an example, if I want to think about ice melting, well, I know that in melting, energy had to be taken in as heat by the ice, so I need a plus sign. Mass of the ice times the latent heat of fusion value. So here's my calculation for the Q required, the energy that the ice has to absorb to melt, divided by the melting temperature. A really easy mistake to make, and again, this is a situation where your calculator is trying to help you out, is of course, if you plug in the melting temperature for ice as it melts into water in Celsius, you're going to tell your calculator that you need to divide by 0, and your calculator is going to tell you that that's undefined. Of course, what you need to do is you need to plug in the melting temperature in Kelvin, which happens to be 273 Kelvin. Let your calculator help you out. Make sure that you get that temperature value in the right units to do this calculation. The second process is thinking about a heat reservoir. So of course, for a heat reservoir, it also doesn't change its temperature. So calculating the change in entropy for a heat reservoir as it's part of a thermodynamic process, well, we need to calculate what's the energy absorbed or released by the reservoir, and then again, what temperature did that reservoir remain at. When we think about our calorimetry problem, energy transferred into or out of the reservoir, when I add that to the energy transferred into or out of the system, both those have to add up to be 0, right? Otherwise, I'm violating conservation of energy. So this tells me that the energy transferred into or out of the reservoir is simply negative the energy transferred into or out of the system. So here's a situation where in calculating the change in entropy for a heat reservoir, I may end up using a specific heat equation even though the reservoir itself happened at constant temperature. So if hot water is cooling to room temperature, well, I know that the energy taken in by the heat reservoir as the water cools is going to be equal to negative the energy that the water gave up as heat. That's negative mass of the water times the specific heat of water times the temperature change of the water. And of course, this was a negative value, right? It's decreasing as it cools. The temperature of the water is decreasing as it cools. So I can basically get rid of the minus sign tucked into delta T and the minus sign out front by simply thinking of this as the hot temperature minus cold temperature for the water. So that's going to give me the energy that the reservoir took in as heat as the water cooled. And so that's what I'm going to plug in for Q. Divide by T. And again, I've got to remember here that the T has got to be in Kelvin. You can get away with having delta T in Celsius. It doesn't matter. The temperature change, you're going to get the same value for the temperature change whether you use units of Celsius or units of Kelvin. But of course, when you plug in that room temperature, that has to be in Kelvin. So the last process that we encounter in calorimetry problems is a specific heat process. I know that the temperature changes during a specific heat problem. So when I think about how the entropy is going to change, I need to go back to this and I need to integrate. Because now the temperature is not constant, it can't simply be pulled out of the integral. Well, Q for a specific heat process is given by mass of your substance times the specific heat of the substance times the temperature change. So if I want to think about some differential element of energy transferred as heat dq, the mass of my substance isn't going to change in any of the problems we're going to work. The specific heat value is constant. The only thing that does change is the temperature. So a differential element of energy transferred as heat is going to be equal to mc times some tiny change of the temperature. The change in entropy in going from state A to state B is going to be the integral from some initial temperature to some final temperature of mc dt over t. And the m and the c come out of the integral, and I'm left with the integral of dt over t. I know that's going to give me the natural log. I can write this out as the natural log of TB minus the natural log of TA, and the property of natural log says that I can combine that into a single term where those two temperatures are given as a ratio. If I use this equation here, TB over TA, again, that ratio may be greater or less than 1 depending on whether or not the temperature increased or decreased. The natural log of something between 0 and 1 is a negative number. So this is perfectly fine, and the temperature values will take care of the sign. Or we can pull the sign out front because, again, we know what the change of the entropy is going to be because the change in entropy will have the same sign as Q. And then we would want to do the natural log of the hot temperature over the cold temperature so that this natural log term is always positive if we've taken care of the sign out front. As an example, again, let's say you've got hot water cooling to room temperature. So we looked at the room side of this in terms of the thermal reservoir. If I want to think about the entropy change for the water, so the change in entropy of the water as it cools is going to be mass of water times the specific heat of water times the natural log of. It ended up at room temperature. It started at some initial temperature that was hotter than room temperature. Or the other option, of course, is I know it's going to be giving up energy as heat, so I can put the minus sign out in front, and then I want the hotter temperature over the colder temperature in my natural log. I got to make sure that those temperatures are given in Kelvin, or else I'm going to end up with the wrong values in my natural log and the wrong answer for the change in entropy.